Welcome to the video help with physics problems for Physics 1A. In this video, we'll be solving the problems in homework set 0. This should be practice and revision of physics you've learnt previously. The first problem is problem 1. In this problem, you're given a velocity time graph and you're for a runner, and you're asked to calculate the acceleration, the total distance, and the average velocity. For part A, it asks you what is the acceleration of the runner, first of all at time 1. To answer this question, you need to study the graph which has been provided in the question. 1 second is here on the time axis. So if we go up here, this tells us that the velocity at 1 second is equal to 2. To find out the acceleration, we're actually interested in the gradient of the line on the velocity time graph. So you should remember gradient is equal to rise over run. So in this case, at 1 second, the rise is 8 meters per second, and the run is, you get up to 8 meters per second in 2 seconds. So that's 2 seconds there. So the run is 2 seconds, and so this gives us 4 meters per second per second. It's worthwhile just checking the units as we go. Meters per second divided by second gives us meters per second, which is the correct units for the acceleration. This is at t equals 1. The question then asks us what's the acceleration at t equals 5. To answer this part, we need to find 5 seconds on the velocity time graph. So that is at this point here. Now at 5 seconds, the runner is running at a constant velocity of 8 meters per second. The gradient of that line is 0, as it's just a horizontal line. So A at t equals 5 seconds is 0 meters per second per second. The runner's not speeding up. And then we want to find the acceleration at 11 seconds. So 11 seconds is here. Now you notice this is a negative gradient. Over this time period, from 10 seconds to 12 seconds, the runner is actually slowing from 8 meters per second down to 4 meters per second. So the runner is slowing down, and we'd expect that the acceleration is going to be negative. So in this case, we've got the gradient is equal to the rise, which is 4 meters per second over the run, which is the 2 seconds, and we've got a negative sign as it's a negative gradient, the runner is slowing down. So this gives us negative 2 meters per second per second. And finally, the question asks us about 14 seconds. At 14 seconds, which is here, we've once again got a horizontal line, so that's got 0 gradient, so the acceleration is 0 meters per second per second. Now generally when we're asked about acceleration, we should actually give a direction as well. In this question that's not actually possible because we're not told in which direction the runner is going. It says it's a straight track. So just the sign is enough because that's obviously forwards or back along the track. Okay, part B. It asks what is the total distance covered. In order to calculate this, we've actually got to work out the area under the velocity time graph. So probably the easiest way to do this is to split it into sections. We've got a triangle here, a rectangle, a trapezium, and another rectangle, and just add all these together. Okay, so the first triangle is for 2 seconds, so the area of a triangle is a half times the length times the height, And then we've got our rectangle, which goes from 2 seconds up to 10 seconds, so that's 8 seconds, and the height is 8. And then we've got this trapezium here, which has width 2, and the height here is 4 and 8 there. So we've got 8 plus 4 on 2 times 2. And then we've got this rectangle here, it's got length 4 and height 4. Okay, you can either do this in your head or on the calculator. We've got 8 plus 64 plus 12 plus 16, and when we add all those up, it nicely comes to 100 meters. Okay, and finally it asks us what's the average velocity during the first 10 seconds. Average velocity. Now the average velocity is just equal to the displacement over the time. So we have to find the displacement in the first 10 seconds, which is in this part here. So we just need to include the triangle and the rectangle. So that is the 8 plus 64, which gives us 72 over the 10. That's meters, that's in seconds. And so this gives us 7.2 meters per second. We notice that we can write meters per second as m/s, or alternatively you could write it as ms with a little -1 as a superscript. So that is how you solve the first question. Problem 2. Now, as you read through a question, it's a good idea to write down in mathematical format what the parts of the question mean. So the question reads, a train starts from rest. We can write that down as the velocity at 0, v0, is equal to 0. And moved with constant acceleration. So let's just jot that down. A is constant. At one time, so we can call this at t1, it was travelling at 30 meters per second. So v1 is equal to 30 meters per second. And 160 meters further on, it was travelling at 50 meters per second. Okay, so let's put this at t2. v2 is equal to 50 meters per second. And the relationship between these is that at t1 it was at some position s1, or we can call it x1 is probably better. Let's call that x1. And then at time 2 it's at position 2, which is 160 meters further on. So it's x1 plus 160. Okay, now part A of this question asks us to find the acceleration. One way that you might think to do this is that acceleration is equal to the change in velocity over time. Now, you can't always use this because this gives you the average acceleration. In this question, that would not be a problem because we're told that the acceleration is constant. However, we don't actually know the time between t1 and t2. So that's probably not the best approach to take in this case. Another way to do it is to use the formula vx squared equals vx naught squared plus 2ax x minus x naught. Now notice that all the subscripts here are x, which is implying that this is just a one-dimensional case. We're only considering motion along the x-axis. Vx squared is the final velocity, Vx naught squared is the initial velocity, and Ax is the acceleration in the x direction, and this is the change in displacement. So we do actually have everything in this equation apart from Ax, which is what we're asked to find. So let's substitute into this formula. The final velocity, which is at time 2, is 50 meters per second per second. Now the initial velocity, we don't actually know how far it's travelled between the initial time v0 and when it has time t2 and velocity v2. So we're actually better off using velocity 1 here as our initial velocity. So we can put 30 squared there, in which case we'll need to use this x0 here corresponds to this x1 here, and this x corresponds to x2. So then we've got plus 2ax, x is x1 plus 160, and x0 is x1. These two cancel out nicely, and so we've got 50 squared, which is 2,500, equals 30 squared, which is 900, plus 2ax times 160. Just rearranging this, we have ax is equal to 2,500 minus 900 over 2 times 160, and putting that into the calculator. Gives us 5 meters per second per second. Now part B of the question asks us the time required to travel the 160 meters mentioned. Okay, so the 160 meters is travelled between T1 and T2. So what we can actually do now is use this formula here, because we have the acceleration, we have the change in velocity, and we're trying to find the time. So time is equal to the change in velocity, which is v2 minus v1. We always do the final minus the initial when we have a change. So the final is v2, and the initial is v1 because that was the velocity at the beginning of this time period, and the acceleration is this a of x, which we've got here. And so substituting in, we've got 50 minus 30 over 5, which is 20 over 5, which is equal to 4 seconds. Now, one thing that we should do as we answer these questions is consider the number of significant figures we're using. In this question, it's not really clear, because v1 here is 30. That can either have 1 or 2 significant figures. v2 has 1 or 2 significant figures. So our answer here, 5 meters per second, has 1 significant figure, which is fine given the starter. We could have also put, or we could put 5.0 meters per second, because it's really not clear from the question how many significant figures we have. So we can put 4 seconds, or we can put 4.0 seconds. But we should think about how many significant figures we're going to use. Okay, part C says the time required to obtain a speed of 30 meters per second starting from rest. So we want to know if it initially has velocity 0, what is time t1? How long does it take to get up to that 30 meters per second? Okay, so to answer this question, we can use this formula again, because we've got the same acceleration, and we know that the change in velocity is the 30 meters per second, because it's gone from 0 meters per second to 30 meters per second. So t is equal to, in this case it'll be v1 minus v0 over the acceleration. The acceleration is constant, so it's always the same. So v1 is 30 minus v0, which is 0 over 5. And so that gives us 30 divided by 5 is equal to 6 seconds, or 2 significant figures if you want, 6.0 seconds. And finally, part D says the distance moved from rest to the time the train has obtained a speed of 30 meters per second. So now we need to calculate the distance. Our formula for calculating distance is x equals x0 plus vx0 t plus a half ax t squared. Okay, so initially it's at the origin, so x0 is 0. So this is 0 plus the initial velocity is equal to 0. So this is 0 times t plus a half times the acceleration, which is our 5 meters per second, times the t squared. It took 6 seconds to get up to 30 meters per second, so this is times 6 squared. So a half of 36 is 18, times the 5 gives us 90. So this is 90 meters. So it's travelled 90 meters along the track in a straight line. And that's problem 2 solved. Okay, problem 3. In this question, we're asked about an automobile and a truck. The automobile has a constant acceleration given by 2.2 meters per second. And the truck has a constant velocity, which means it's got no acceleration, of 9.5 meters per second. Sorry, meters per second. So I'm using the subscript A for the automobile and T for the truck. In part A, we're asked how far beyond the starting point will the automobile overtake the truck. Now in a question such as this, it's useful to sketch a graph to show what we know. So let's here sketch a time versus displacement graph. Now at time 0, they're both at the same point, as this is when the truck is overtaking the automobile. Now the automobile has a constant acceleration, so its displacement time graph is going to be a parabola like this. So this is the automobile. The truck has a constant velocity or speed, so it's going to have a straight line on the displacement time graph. So this is the time at which they overtake. We're asked to actually find this distance, but if we find the time, it will be easy to find the distance from that. So let's try and put what we know into some more equations. So we know the acceleration of the automobile. Let's write down an expression for the velocity of the automobile. The velocity of the automobile is just the integral of the acceleration. So it's a dt, which is the integral of 2.2 dt. So that's 2.2, it's 2.2 t plus some VA naught, the initial velocity of the automobile, which we're told it starts from rest, so that's just 0. So the velocity of the automobile is given by the expression 2.2 t. Now, we're actually interested in when they're at the same position, so we also need an expression for the displacement of the automobile. So to get displacement, we just have to integrate the velocity. So this is the integral of 2.2 t dt. Integrating this, we get 1.1 t squared plus the displacement of the automobile at time 0. We're told that at time 0 is just when they overtake each other the first time, so we're taking that as our 0 position. So this is equal to 1.1 t squared. Now for the truck, we've got the velocity of the truck and we need to find out the displacement of the truck. So this is equal to the integral of the velocity of the truck. So that's 9.5 dt, which is just 9.5 t plus xt naught. At time equals 0, they're at the same position, which is x equals 0. So this is equal to 9.5 t. So now we've got an expression for the position of the automobile and the position of the truck. When they're at the same position is when they're going to overtake the second time. So we can put 1.1 t squared is equal to 9.5 t, cancel a t from each side, and that tells us t is equal to 9.5 over 1.1, which when we do it on the calculator, we end up getting 8.64 seconds. Now the question didn't ask us what time did they overtake it, did the automobile overtake the truck. It asked us how far along the road. So now we need to substitute this time back into either this equation or this equation. Doesn't matter which one we choose to get the position. So let's substitute it into the automobile equation. 1.1 times 8.64 squared. And when we do this on the calculator, we get 82 meters. Now, in this case, as the acceleration we're given has two significant figures, and so does the velocity, our answer should have two significant figures. So that's why I've written two significant figures here. As we do working along the way, it's useful to keep all the significant figures, so that's why there's more significant figures here. And then at the end, just make sure that you give your answer to the same number of significant figures as the least number of significant figures in the information in the question. Okay, so that's part A done. In part B, it asks us how fast will the car be travelling at this instant. Well, we've got the instant now, and we've got the equation for the velocity of the car here. So the velocity of the car is equal to 2.2t, which is 2.2 times 8.64. When we do that on the calculator, we get 19.00, so we just write 19 because that's two significant figures, so meters per second. And that's the answer to question 3. Okay, problem 4. Now in this problem we have a particle moving along the x-axis, and its equation is given by x equals 50t plus 10t squared, where x is in meters and t is in seconds. Now we're asked to work out things about the velocities and the accelerations. A good way to start this question is to derive formulas for the velocity and the acceleration. To get the velocity, we just need to take the derivative of the displacement. So the velocity is equal to 50 plus 20t, and the acceleration is the derivative of this velocity. So when we take the derivative of a number, we get 0. The derivative of 20t is given by 20. So this will be in meters per second, as this is an acceleration. Okay, now let's look at what we're actually asked to calculate in the question. Part A says the average velocity between t equals 1 and t equals 2 seconds. So the average velocity is equal to the displacement over the time. Okay, so what we need is the displacement at 2 seconds minus the displacement at 1 second. That will give us the change in the displacement. It should actually say change in displacement over the time, which is the time interval is from 1 to 2 seconds. Okay, so we need to calculate the displacement at 2 seconds and at 1 second. So we just substitute in here. x2 is equal to 50 times 2 plus 10 times 2 squared. So this is 100 plus 40, so this is equal to 140. And the displacement at 1 second, we substitute in 1 here. So this is 50 plus 10, which is equal to 60. Okay, so we can substitute these numbers into this formula here. So we've got 140 minus 60 over 2 minus 1, which is 1. So 140 minus 60 gives us 80. And that's a velocity, so that's meters per second. Now part A also asks us to calculate the average acceleration. So this is equal to the change in velocity over the time period. We can put delta t if we want. So this is the velocity at time 2 minus velocity at time 1 over t2 minus t1, which will just be 2 and 1 seconds. Okay, so the velocity at 2 seconds, we just substitute in 2 seconds in here. So this gives us 50 plus 20 times 2, which is 50 plus 40, that's 90, and meters per second. and the velocity at time 1 is equal to 50 plus 20, which is 70 meters per second. Okay, so we can substitute these in here. We've got 90 minus 70 over 2 minus 1, so this gives us 20 meters per second per second. Okay, in part B, we're asked to find the instantaneous velocities and instantaneous accelerations at t equals 1 and t equals 2 seconds. We've already found the instantaneous velocity at t equals 2 and t equals 1 seconds up here, so this part's easy. We've got v2 is equal to 90 meters per second, and we've got v1 is equal to 70 meters per second. Now, to find the instantaneous acceleration, we just have to look at our acceleration formula. The acceleration is actually always constant. It's always equal to 20, so it doesn't matter about the time. So we've got the acceleration at time 2 is 20 meters per second, and the acceleration at time 1 is equal to 20 meters per second. Now, that's answered part B. Part C says compare the average and instantaneous quantities in each case and explain why the larger one is larger. Okay, so here's the average acceleration, the average velocity, 80 meters per second. At time 2, the velocity is 90 meters per second, and at time 1, it's 70 meters per second. Now, the velocity is greater at time 2. As we can see, this is accelerating, so it's getting faster. We'd expect the velocity to be greater then as the time progresses. So at a later time, the velocity is always going to be larger. So, and with the acceleration, as it has a constant acceleration, this acceleration and this acceleration are going to be the same. We would have made a mistake if they were not. So that's the answer to problem 4. Okay, we're up to problem 5. Now, in this problem, we have an electron with velocity Vx naught is equal to 1.0 times 10 to the 4 meters per second, which enters a region of width, so this width is equal to 1.0 centimeters, and it's accelerated in that region as there's a potential difference across here which will make a charge accelerate, and it emerges with a velocity equal to 4.0 times 10 to the 6 meters per second. And we're asked what's the acceleration. And we're told that we can assume that the acceleration is constant. So in this case, we need to use the equation that Vx squared is equal to Vx naught squared plus 2ax times x minus x naught. X naught is here, so this is x naught, x is here, and this is 1 centimeter further on from x naught. So this is x naught plus 0.01 meters. Okay, so now we can substitute everything into this equation here. And the only thing we don't actually know is this acceleration, which is what we're hoping to find. So we've got 4.0 times 10 to the 6 squared is equal to 1.0 times 10 to the 4 squared plus 2ax times x, which is x naught plus 0.01 minus x naught, which is x naught. Okay, these x naughts cancel out. Note that I've changed from centimeters to meters. As these speeds are in meters per second, not centimeters per second, we need to make sure that we have consistent units throughout everything. Okay, so now all we have to do is rearrange this to get our answer. So we have 0.02, that's 2 times 0.01 times the acceleration is equal to the difference in these two. So we can, if we do it on the calculator, 4 times 10 to the power of 6 squared minus 1 times 10 to the minus 4 squared, this is equal to 1.5999 times 10 to the 13. And so the acceleration is equal to this divided by this, which is equal to 7.9999, so that's 8.0. So we're going to go for two significant figures, as that's what both Vx0 and Vx are given to. So 8.0 times 10 to the 14 meters per second per second. Okay, and that will be in the x direction. And the x directions, the direction shown in this diagram is along this path here. Okay, that's the solution to problem 5. Problem 6. Okay, in this problem we have a rocket which is fired vertically with a constant acceleration, and then its fuel runs out, so we have gravity acting on it, causing it to fall back towards the Earth, and we need to find out the maximum height and the time elapsed. With this question, a good approach to take is to draw a diagram. We want to draw a time versus altitude diagram. So initially it's accelerating upwards with constant acceleration, so that's going to be a parabola shaped like that, and we can label this t as t1. We know that's 60 seconds because it accelerates constantly for the first 60 seconds. Once it's accelerated to this height, its fuel runs out, and we'll assume that gravity is acting on it with constant acceleration. Later in the session you can come back and have a think about whether that's an appropriate approximation or not. But yeah, now gravity works on it, slowing it down until it reaches some maximum height here. So this is the maximum height. We'll label this height as h1, and this can be h2, which is the maximum height and happens at time 2. And then the rocket falls under the influence of gravity, accelerating back towards the Earth, and it hits the Earth at some other time, t3 here. Okay, so in part A it asks us what's the maximum altitude, so this is what we're trying to work out. And in part B we need to work out this t3 here. Okay, so let's just write down a few things we know. We know the velocity here at time 2 is equal to 0. So at maximum height, its velocity is 0 meters per second. That's when it turns around and its velocity changes direction. So right when it's changing direction, it has no velocity. Okay, let's work out the velocity at this time here, and also this first height, because we might find these things useful. So we have that the acceleration initially is equal to 20 meters per second, and so the velocity here is under constant acceleration, so that's just 20 times t, and that's equal to, t is 60, so that's equal to 1,200 meters per second. So v1, 1,200 meters per second. And now what we're asked to find out is this height here. So what we can actually use is the equation x is equal to x0 plus the initial velocity times the time plus a half ax t squared. And what we're interested in looking at is this time period here. So we're going to need to know the initial height at this period, which we do know. We'll need to know the initial velocity, which is here, and we'll need to actually know the time lapse here. So to work out this time lapse, between here and here we have a constant acceleration. So we can use acceleration is equal to the change in velocity, so v2 minus v1 over t. And we have the accelerations minus 9.8. The final velocity is 0. The initial velocity is 1,200 meters per second upwards. And the time is t. This tells us that the time from here to here, when we rearrange it, is equal to 1,200 divided by 9.8, which gives us 122 seconds. So this is 122 seconds. So this time t2 is 60 plus 122, it's 182 seconds. So now we've got the time interval between t1 and t2. We also actually need to know the height here. So what height has it reached when it finishes accelerating? To work out that, we can use this formula here, but we use it for the time interval from 0 to t1. Okay, so the height h1 is equal to the initial height, which is just 0, plus the initial velocity. Initially it's actually got 0 velocity, plus the acceleration, which is a half times, we're told it accelerates at 20 meters per second, and we're told this goes for 60 seconds. So when we do that on the calculator, we get 36,000, which is 36 kilometers. So here we go, let's just write this as 36 kilometers. Okay, so now we're considering the time interval from here, from t1 to t2. We actually use the same equation, but this t1 is our initial time and t2 is our final time. So h2 is equal to h1, which is 36,000, plus the velocity at time 1, which is 1,200, times this time interval, which is 122, and then plus a half axt squared. Now the acceleration is actually acting downwards now, so that's a negative acceleration. So it's minus a half times 9.8, which is g for Earth, times the time interval over which that's working. And when we do that on the calculator, we end up getting 110 kilometers. So this height here is 110 kilometers. So that's our answer to part A. For part B, we're asked to find this time here. So we've got the time from here to here, 60 seconds, and from here to here. So we've got that time. Now what we need to work out is the time for it to get back to Earth. What we know is the initial height and the final height. It starts 110 kilometers above the Earth and ends up on the Earth's surface. So we can actually use this formula again and solve it to find t. So the final height is 0. The initial height is 110 kilometers. The initial velocity up here is 0. So we've got plus 0, we can ignore that term. And the acceleration is minus 9.8. So we've got minus a half times 9.8 times t squared. Okay, we can rearrange this. So t squared is equal to 110,000 over a half times 9.8, so that's 4.9. And solving that on the calculator gives us that t is equal to 150 seconds. So that t is this interval in here. And so t total, which is t3, this t that we want, is the 150 plus t2 was at 182, so we can add the 182 onto that. And when we do that, we end up with 332 seconds. Now, this has 3 significant figures. I think the data in the question was only given to 2, so we should write this as 330 seconds. Okay, and that's the end of this problem solving set.